So this is Jason Stauth. I'll be giving this talk. This is a webinar that's presented by the Power Management Integration Center. We are a National Science Foundation Industry University Cooperative Research Center, so jointly subsidized by the NSF, but supported by industry through industry memberships. We are joint between Dartmouth College, which is where I am, and our director, Charlie Sullivan, is, and UC San Diego, where we have Patrick Mercier and Han-Fu Clay involved over there. And I will mention that we have memberships available for interested industry partners who are, if you're interested in joining us and learning more about our research, guiding research projects, getting access to students and faculty. We have another meeting scheduled for June 22 and 23 in Boston this year, so feel free to get in touch with us if you are interested. So I'm Jason Stauth, and I am a professor at Dartmouth. I've been here for about 15 years. Most of my career, I have been working in this area of electronics for energy and power management, and especially in the area of hybrid and resonant switch capacitor converters. And so that's mostly what this talk will be about. And feel free, there is a Q&A section. So as I'm talking, if you want to write questions into the Q&A, I will answer those at the end of the talk. And I will mention this talk is recorded, and there is a chance we will post that, but it may take a little while for that to show up. So just to get right into it, this talk is about DC-DC converters, which are electronic circuits that process energy and convert voltage from one level to another. And the goal is to do that without losing energy and to do that with low cost and small size. So when we're talking about efficiency or not losing energy when we do this, there are several factors. One is the loss due to the conduction of electrical current, which we would ideally like to be small. Other considerations are the loss due to simply operating the converter at some frequency, and then any static or additional losses in the circuit. And then when we talk about making DC-DC or other power converters small, we think a lot about density. So density being the semiconductors or the power devices that we use to switch and move energy around. And that has to do with volumetric and area-specific energy and resistance. We have the energy density of passive components, typically inductors and capacitors, but also other potential passive components we might use to process energy. And then frequency, which is if we have a lot of energy storage, we can typically operate at a lower frequency and provide the same amount of power. And the final is the utilization of each of these components, whether they're passive components or active components. We want to use the maximum capabilities of those to do this job the most effectively and efficiently. So to do this, one strategy is to operate at higher frequency. So higher frequency, again, allows us to use smaller passive components or less total energy storage. But the drawbacks of going to higher frequency tend to be increases in loss, frequency-dependent losses, whether those are in the passive components or the semiconductors themselves or even the control circuitry itself. So a lot of work in the last 15 to, I should say, most of the life of power electronics has been exploring architectures that can get around some of these challenges, reduce the needed storage in passive components, and move energy more efficiently through having better utilization. And that's where the new-ish trend, I say new, but it goes back a little ways, of using both capacitors and inductors to transfer and move energy. So hybrid or resonant switch capacitor converters use what we will describe as a switch capacitor stage and an inductive stage. The switch capacitor stage uses the high energy density of capacitors to step voltage down and reduce the energy that the inductor needs to process. While the inductor eliminates certain loss factors in the switch capacitor stage that we often describe as charge sharing or hard charging losses, which relate to impulsive charge flow that's in resistively limited charge sharing loops in the switch capacitor stage. If we add magnetic energy storage in between, we can eliminate that. And this allows us to have overall higher efficiency and hopefully higher power density. And the two of these we ideally like to trade off to gain either smaller size or lower loss or combinations of both. So the most common hybrid DC-DC converter example would be what we often describe as the three-level converter or the three-level buck, which has a single flying capacitor and a switch network where the switches block half of the input voltage, and the flying capacitor also stores half of the input voltage. And across a switching cycle, we turn on switches in a way that presents half of the input voltage to this, what we call switching node Vx, that's presented to the inductor, and then potentially applying a pulse width modulation phase where we're connecting the inductor to ground, much like in a buck converter. And then another phase where we connect the switching node to half the input voltage through the flying capacitor, and then potentially again pulse width modulating. And across these two cycles, making sure that there's a net zero charge that flows into the capacitor, which must remain balanced. And in fact, the balance of the value of this flying capacitor voltage is very important, because if it's not exactly, in this particular case, Vn by 2, then the switches are exposed to a larger voltage, which can lead to voltage stress and lead to challenges. But if this does work, what it provides is a lower voltage supplied to the inductor, which reduces the current ripple, therefore allows us to use either a smaller inductor or have lower ripple. It also multiplies the effective frequency seen by the inductor, because across a full switching cycle where each switch is on and off only one time, the inductor sees two pulse width modulation periods, and therefore that also can reduce the voltage or the current ripple in the inductor, allowing it to be even yet smaller. And so those are the central advantages seen in the three-level converter, which is, again, the simplest example, but really highlights a lot of the challenges that we'll talk about later in this talk. In general, there are quite a few different topologies and increasingly complex switch capacitor stages, and potentially even with multiple inductors. But the generic scenario looks very similar to this three-level, just that we may have a lower voltage conversion, lower switching node voltage, depending on how we operate the switch capacitor stage. And we can do many different things, and I'll talk about some of those topologies coming up. But going back through history, I like to bring it up because the concept is not sort of new as of 2025, 2026. This has been showing up in the literature going back at least as far as I can find, reasonably and similar to what we're doing now, to 1988 with Robert David Middlebrook, some call the father of power electronics himself, has a paper where he's presenting what I would call a series parallel hybrid switch capacitor true converter, which itself is actually quite interesting. But more interesting, I think, is that this was lost to the sands of time, but now it looks very similar to things we're doing now. And then if you go back even 30 years to the medium and high voltage power conversion literature, we see multi-level inverters, multi-level DC-DC converters and rectifiers that leverage hybrid and resonant switch capacitor concepts. For example, the flying capacitor multi-level converter, traditionally thought of as an inverter, has been used in medium and high voltage applications for a long time, largely due to its benefit, which is that it can use low voltage rated switches to address a high voltage supply and convert that across a wide conversion ratio. So it was really the lack of high voltage switches and the need to process energy had led to hybrid type topologies many, many years ago. And that includes the early 2000s with the modular multi-level converters, which are themselves a switch network, a switch capacitor, or switched galvanic energy storage network, could be also a battery, to help low voltage switches process high voltage across a wide conversion ratio. And so that's interesting, but I think also indicates why we're looking at these types of converters now, even at lower voltages, even at voltages that are completely contained on a low voltage integrated circuit, is because it allows us to use low voltage switches to address high voltages and higher conversion ratios. It also, as described before, leverages the high energy density of capacitors. And increasingly, as we're going forward, and it really is the trajectory of technology and history, there is an increasing tolerance for complexity to achieve performance benefits. And so while these are relatively more complex than conventional buck or boost type DC-DC converters or historically AC, DC to AC converters, that tolerance is okay as long as eventually we figure out and address some of the challenges. And obviously, one of those challenges is control. But before I get into control, just briefly talk about just a perspective on topologies. We like to, I like to describe these as a sort of there's a basis set of switch capacitor stages where there are the two base classes, the series parallel and the Dixon's ladder, Cockcroft-Walton, which all have a similar switch network. Define this performance envelope where the series parallel is known to have this best passive component utilization, meaning it uses passive components the best. For the same volume of energy storage and passive components, it can provide the highest charge transfer or current delivered per phase, which is a very nice feature. So it can use smaller passive components and while providing the same output power, while the Dixon ladder, Cockcroft-Walton have the best active device utilization, which then for the same switch area can achieve the lowest resistive conduction losses at a given conversion ratio. And all the other topologies sort of have aspects of each of these built into them and have benefits and trade-offs of each of them. But they help map out sort of the performance envelope of the different topologies and really what it, in our analysis, and I think others, there's no real best topology. There are just topologies that are well suited for a given application and set of constraints. And so the flying capacitor multi-level has gained a lot of traction despite being sort of intermediate in both passive and active utilization because it gives very nice control features, such as multiple different conversion ratios that are easily scalable across the full conversion ratio range. It also has this multiplication of effective frequency. It actually uses the inductor, has good utilization of the magnetic component, even if it has less good utilization of the capacitors. Whereas other topologies, such as sometimes called a doubler, sometimes cascaded, gear, exponential, really simply put, nominally 2-to-1 stages cascaded can give the highest conversion ratio per unique component. So if you're limited by sheer numbers of components, this can give the highest conversion ratio per component. Can be a very nice feature in some contexts. And so some new topologies leverage a piece of one and a piece of another to achieve some benefit. And an example of that is the series capacitor, sometimes called double step down, actually originally called double step down converter back over really 20 years ago, introduced by Nishijima, which is related to the Dixon topology. In other words, it uses switching devices very well, but it goes a step further, replacing output coupled switching devices with a unique inductive element. And it actually outperforms the Dixon in the sum VA, meaning current handling capability, but with the trade-offs of limiting the conversion ratio range and requiring those multiple inductors, but still gaining significant traction, especially recently for point of load high current density applications. So just to mention that, and this is my last sort of topology discussion. This is not a talk about topologies, but just to mention them. because there has been a bit of a growth, or I might even say an explosion in topologies in the last few years, but where do they all fit in is somewhat important to discuss. One recent topology class is the, as we call it, or some call dual path converter, which is a type of similar to a hybrid converter where we use a parallel hard switched capacitor path with the stated advantage of reducing the inductor current. And by, as stated, reducing the inductor current allows you to use a smaller, higher ESR, higher loss inductor. And frankly, there are many other topologies and some very nice analyses of these topologies. I would point to these two papers where these are described and how they fit into the overall topology class of hybrid topologies. I just do have to plug one recent analysis where we look at this, and it is complicated. There's, again, as I say, there's no best topology, and for a given topology to make sense, it must fit with the operating scenario, and in this particular case, the dual path with a hard charging path, that hard charging loss must be factored in. And in fact, our analysis shows that the hard charging loss path must be significantly lower effective resistance than the inductor resistance to make sense in most scenarios. So, okay, moving on and back towards just conventional hybrid topologies and talking about control. So the unique difference between what I would call hybrid switch capacitor topologies and conventional magnetic topologies, or most conventional topologies, is the fact that they have a high order, or at least non-zero order switched capacitor network in the system. So if we were to look at a pure switch capacitor converter, the case is that there are rigid voltage loops. There's KVL forces the capacitor voltages to be a very specific value. There's no value they can be other than a very specific value in steady state. And so they are typically balanced with 0 to first order balancing dynamics. However, when we take a switch capacitor network and hybridize it, meaning we achieve, and we use Robert Palawa's coined term, soft charged, meaning there's no impulsive CV squared loss in the switch capacitor network. When we do that with an inductor, what happens is we decouple those flying capacitor voltages. And so they are allowed to have independent energy storage. Independent energy storage means we have more poles or eigenvalues, or we have higher order dynamics. And these higher order dynamics are really, if we talk about the control of hybrid converters, this is the elephant in the room. This is the main difference between hybrid converters and most other power converters. So we need to mitigate balance. Otherwise, it can lead to overstress of switching devices and potentially failure. And an example would be the flying capacitor multi-level converter can have, if it's in quote unquote N level, so I showed the 3 level, but you can extend that, has N independent energy storage elements, so N poles, so 5 level FCML is a 5th order system. And that's very different than a conventional buck converter, which is a second order system. So a PID converter is not well suited to regulate a 5th order system. So the dynamics of voltage balance, again, one of the challenges with voltage balance dynamics is not that it's basically that those poles tend to be at very low frequencies and the balancing tends to be very slow. And so capacitor voltages can drift from their nominal states, and this can come from slight duty cycle mismatches or source or load impedance or transients in the converter, resulting in higher current ripple, higher voltage stress, potentially failure. In some scenarios, and frankly, in most scenarios, there is a weak negative feedback. In other words, that these balancing modes or eigenmodes are damped by some system ESR, but again, this can be slow and take a long time, and it's also weak, so it may not be able to compensate for the duty cycle variation, the source or load impedance. So often we do need active feedback to achieve balance. And again, one of the signs of imbalance is that switching node, which is presented to the inductor, is normally supposed to be at some prescribed value, but if it's imbalanced, it will often be all over the place. And that's a sign that your switches are experiencing high voltage stress, and your voltage ripple will have subharmonics, and there's all kinds of bad things about having imbalance. So going back, this is not a new observation. This goes back to almost really early in the days when, after the flying capacitor multi-level converter was being explored, these high order dynamics were explored as well. And there's many works in the literature that study this, and also ways to mitigate voltage balance. But I will mention that this is an issue with all conventional hybrid topologies, and many people will say, I have a new topology and, oh, don't worry, it's self-balancing. But if you're soft charging a hybrid converter, you will invariably have some consideration of balancing of that flying capacitor voltage. And maybe the natural balance is sufficient, and in many cases it is, and that is okay. But there are many scenarios where it is a challenge, and one being even just starting up a hybrid converter is an extreme imbalance scenario, because you need to bring a flying capacitor from probably 0 volts to some value. And so you would like to do that as fast as possible so that you can start up quickly and make sure there's no voltage stress during that startup. So balance is a problem regardless of mostly what topology you have. And so one study of this, and this is again of my group, and there are many, I'm mostly obviously talking about the work of in my group here, is we use a perspective of modern control to study balance. And why we like it is because, well, it sounds complicated, but it's very straightforward. I'll try to I won't really go through any linear algebra, maybe a tiny bit, but it's just fairly straightforward concepts that lead to very simple conclusions. And so one of these observations, or one of these studies, is the concept of observability and controllability. We think of this as they're both basically quite related. Observability is, so we have a switching voltage we're applying to the inductor, and if we are to look at that across the switching period of the converter, are we able, from those measurements of that switching voltage, to be able to determine all the flying capacitor voltages? Then if we are able to do that, it's observable. We know what the state is of the system. Controllability is just a binary metric. Is there any current we can apply, or any control action we can apply, charge flow through the inductor, that can force those capacitors to be balanced? Then it's controllable. It's pretty straightforward. And actually the analysis and the conclusions are straightforward as well. So here's an example of the 5-level flying capacitor multi-level converter. Just do it at the duty cycle of 1/4. How we study this is we look at, so the flying capacitors have sort of integer fractions of the input voltage when it's normally operated. I'm not really going to go through how this works too much. I'll just really mostly focus on this as a prototype for the modern control. We can look at the switch voltage as a function of the capacitor voltages in state 1. VC1 is connected to Vx, so Vx is equal to the voltage on flying capacitor 1. In state 2, the switch node is VC2 minus VC1. We write that down. In state 3, it's VC3 minus VC2. And in state 4, it's Vn minus VC3. That's the switching node voltage. If you do the math on those, if these are those integer weighted voltages, that Vx will always be 1/4 of Vn. Okay, so what we're going to do, this is basically the limit of the complexity of linear algebra. I'm just going to put these into a matrix. So say across that switching cycle, write the switching node voltages, and as a function of the flying capacitor voltages and the input, and we get a matrix. We call this the output connection matrix. It's actually just ones and minus ones, saying here VC1 is Vx is VC1, here Vx is VC2 minus VC1, etc. And it will turn out if this matrix C, we call this the output connection matrix, if we can invert this matrix, then we should be able to know what these capacitor voltages are and the input voltages as a function of those samples. In other words, this is like n equations and n unknowns. If we have as many equations as unknowns, we should be able to solve for these capacitor voltages. We describe that as, so if we can invert C, then it's full rank, then the system is observable. From samples of Vx, we know the voltage of the capacitors and we know Vn. And we should be able to know that in one single converter period. And eventually that ends up, there's a formal proof of observability, but it comes down to this. It's not really that complicated. It's n equations, n unknowns, it's observable. For controllability, the way we think about it is, so there's some charge that flows through the inductor, and controllability is a binary metric. So I'm not even going to say what is that charge or what did we do to make that charge flow, but say we can do something to make some charge flow. There's charge that flows in each of these periods, and in each phase, it's going to either discharge or charge the capacitors. And actually, each capacitor must be charged and discharged in a given cycle, or else the system's not in steady state. So we can say from a current flying capacitor voltage, plus how much it gets charged and discharged gives us our new flying capacitor voltage. And it turns out this is what we call the state connection matrix, because it just tells us how the charge impacts the flying capacitor voltages. If this is full rank, this matrix, the system's controllable. And that means there is a way to balance it. And that also means the system will be naturally balanced, or we also proved that as well. And so that's basically the level of complexity of how to analyze, does your hybrid topology have a balancing issue, and is it balanceable? But we can, we put this in a full state formulation, and I'm not going to go through it too much, but just saying we keep track of the flying capacitor voltages and the switching node voltages, and those matrices we talked about show up there. And if, again, they're full rank, the system will be controllable and observable. And it will turn out those are basically should have the same rank. They're related. So if it's observable, it's controllable, and vice versa. And so we can use this concept to study whether we can achieve regulation of those flying capacitor voltages in the hybrid converter. Another use case is that we can use the modern control concept, to build things like state observers or flying capacitor voltage estimators. And so we also showed that you can do that with the 6-level FCML. We built a state observer where we're measuring the switching node voltage. It looks complicated, but it's really simple. We're just inverting those equations that I showed you before. It's actually super simple. It's like I'd say middle school math. It's nothing, not really, we don't really even invert a matrix, but we can, by those samples, we can invert and find flying capacitor voltages and the input voltage. The only thing that's slowing it down is we have a filter, digital filter, that kind of makes sure that our samples and any noise in our samples is not a problem, but we get really good estimate of those flying capacitor voltages in a very short period of time. And then we can also do this when duty cycling between levels. I didn't really go into it, but the FCML has many conversion ratios, so we can duty cycle between like the lowest switch cap level and ground. That's this one. Or we can duty cycle between the lowest 2 switch capacitor levels. And what's interesting about this case is that we actually get more information when we're at intermediate levels, because every other cycle we're connected to those flying capacitors and we get information. And so we see that when we're at these intermediate levels, we actually settle faster than when we're at like one of the edges. Okay. And then I will mention, Professor Palau at Berkeley and his group did some nice work on even a more complicated version of this for a multi-level inverter, where those equations are always changing. So there's not but as long as you keep track of what the equations are, it's very easy to invert them, gather the information, put it into a filter, know what all your capacitor voltages are. and your input voltage. It's kind of convenient. Um, so kind of extending beyond this, there's one next level of kind of interesting work we did was on this notion that so controllability and observability are binary metrics. In other words, they're either true or false. There's not something in between. And that can be a little misleading because it can tell you, for example, the 5-level FCML is not controllable at this duty cycle 2 by 4. I won't really go into it that much, but that matrix C is not full rank there. And it tells you right up to the edge of that level that it's still observable and controllable where you know it's getting bad. The other thing is that right near duty cycle of 0, if your duty cycle is 0, that means you're not even connecting the switch capacitor network. Your V out is ground. And that's not controllable or observable either because you have no access to the capacitor, so you can't do anything. So what we know that around these levels that controllability and observability are not really good metrics. We introduced this new metric. We call it the condition. Well, the condition number is a well-known concept in linear algebra, quantifying how full rank is a matrix. We extended that a little bit to give a better perspective for these types of scenarios. And it basically we use singular values of those same matrices, which you could think of it as the solution to a system of equations. If one solution goes to infinity and one goes to 0, you know that system of equations is kind of on the edge of being solvable. And so these singular values are kind of like a representation of those two solutions. And so if you have one going very large and one going very small, it's less either observable or controllable. And so we use this as a metric, and it tells it, so the lower, the better here. And it shows that okay, around non-controllable, the condition number, this metric, which by the way, is just a snap in MATLAB. You just, single value SVD of matrix in MATLAB just pops these out. They're not, do it by hand or anything, but it basically can tell you how observable, how controllable it is at a given conversion ratio. And it is interesting, and it does tell you information. For example, it tells you in that 5-level FCML, your observer will be faster at that duty cycle where you're in between levels because you get more access to information. Whereas when you're duty cycling between one level and ground, you have less information. So condition number is better. So there's kind of some interesting information you get out of it. And so we like it. It's sort of an interesting thing. We can also use it to show scenarios where we can fix non-controllable conversion ratios. So for example, we have ways of modifying the switching sequence. I didn't really go into it here, but they're in this paper we go into. I'm not going to go into it too much, but basically if you have a converter and you have a not controllable scenario, it's not going to be balanceable. It's going to be unbalanced. It's actually really bad. But if you change the way you switch the capacitors, there are ways to fix that. I'll just say that. And so this particular way, we can show, oh yeah, we can fix it and it's not that bad and it's still controllable. And so it's just a nice, very quick analysis to show, is your converter good or bad? What's that switch capacitor network look like, and how is it going to work? We can also use this analysis to compare topologies to say which one will be better for balancing than another. And so an example being that series parallel converter. If you think about the series parallel converter, in one state, all the capacitors are in series between Vn and the switching node. Next state, they're all in parallel. Because they're all in parallel, they're forced to have the same voltage. So that means I've heard people say, oh, the series parallel doesn't have a balancing problem, but it does. It does have a balancing problem, but it's not that bad, not as bad as some, because these capacitors all have the same voltage. You just don't know what exactly that voltage is. It actually looks a lot like the 3-level buck. These capacitors sort of behave like a single capacitor. It's not quite the same because the capacitance is larger in this phase as presented to the inductor than in this phase, we talk about the complexities a little more in this paper, but basically it means there's an order reduction and it has good balancing dynamics. So series parallel balances is probably the best balancing hybrid topology. So it balances pretty easily. But we can look at all these other topologies, and again, with this condition number, lower is better, lower is better. And so it shows, series parallel, and there's some other topologies like Fibonacci and some flavors of Dixon where the capacitors are sort of they're both dependent, but they're all sort of in parallel, and it simplifies the effective balancing dynamics. And so it makes it so that those should be controllable, easy to control, easy to balance. And so this is just a nice feature. We can compare topologies. And whereas, for example, FCML gets worse the more flying capacitors we have, that probably makes sense. And some other features, just different flavors of Dixon have more or less challenge with voltage balance. Now, just getting back into sort of active control. So now getting back into, now we want to build some control, some feedback, some loops to regulate those flying capacitor voltages. The reason in some ways control for hybrid converters is not that bad is that if you can ensure voltage balance, you can pretty much use any controller you want. So you can use PID, type 3, current mode, voltage mode, nonlinear control, anything. The problem is you do need most likely some form of active balancing. So the active balancing really is the key. And there are many ways that have been explored in the literature. I'll kind of go through several of the main ways. So the simplest way is, and frankly, this is not a terrible idea. It can work and can be done, is just measure the flying capacitors and force them to be balanced. So you can use some type of linear regulation, active clamp type feedback to make the voltages be what you want them to be. And there are scenarios where this does actually make sense. We have an ISSCC paper this year that has a very challenging balance scenario where we do something like this for various reasons. The problem is that it's not great for most cases because if you have systematic imbalance, this will just be lossy and it's not going to solve that systematic imbalance. So it may not be desirable. So most active flying capacitor balance uses the switching node, or most of the time we are looking at this switching node, the node that's presented to the inductor, because typically it's readily available to us. Again, it provides information of all the flying capacitors, presuming it's observable. And the basic goal is, and it's actually the balancing problem is pretty simple if you look at it. If you're looking at the switching node, if the switching node is too high, that means you need to take more charge out of that flying capacitor network in that state. If the switching node is too low, then you want to take less charge out. So if you take less charge out, you're not going to discharge whatever was undercharged in that network. And if it's too high, you're going to reduce that voltage. And it can be proved that that action is actually, that's as complicated as it is. That is just true. You may also need to factor in the polarity of the inductor current. Some cases, like an inverter or other scenarios, if the current is negative, you might need to think about that. But basically, you want to discharge a high switching node, you want to less discharge a low switching node. And so some early examples of doing this, going back 10 years or so, were basically just so if our switching node, we're imbalanced, if our switching node is too high, what we do is we increase the duty cycle here. And if switching node is too low, we decrease the duty cycle. And you can show this type of thing works, but as described here, and frankly, this is a paper out of my group, this concept doesn't work that well. So it can lead to limit cycling behavior, there are underlying dynamics. There are sort of like integral control dynamics. So if you change a duty cycle permanently, that flying capacitor voltage can sort of wind up. It will integrate that change in duty cycle. And so it's not quite so simple as just make the duty cycle longer, make it shorter. But this was a noble and interesting effort. We showed you can do that. The more recent and probably one of the more mainstream strategies to do voltage balance is based more around what we call a current mode type control or current limit control. And often we describe it as valley current control. It actually can work whether it is peak current mode control or valley current mode control. We typically do valley current mode control. There's some stability benefits, or frankly, peak current mode control has some stability problems that you have to consider. So valley current mode control is the more common method. The idea is instead of looking at the switching node, we look at the inductor current. And now if we force the low current to be the same in steady state, what happens is that it forces the flying capacitor voltages to balance. And why that is actually I can explain it pretty simply. If we say the valley current is always the same, then if for some reason the switching node was high, it's going to ramp the current up more, and more charge will flow out of the switching node when it's at the high state than it will at the low state. And over time, this forces it towards balance. And sort of with that simple perspective, in fact, if you make those approximations, which is pretty much just a small ripple approximation, my students, Kishle, Datta, and Avinash, can show it's basically just follows like a discrete time eigenvalue. The voltage imbalance just decays. We know exactly how fast it decays. It's actually still not very fast. So current mode balancing is still relatively slow. Depends on a few factors, but it is quite practical and functional. And there's some nice work on this. I should point out the paper from University of Padova that has a nice analysis of the stability of this valley current and actually also peak current mode control, and shows how that works and what you need to do to make that work. The other types of control that we have been exploring more in our group are more voltage mode control and tend to be nonlinear control. So one of our favorite types of control, we call it like a stress limit control, which is frankly, you can view it as a form of an adaptive on time or model predictive control, where basically we set a switching threshold for the switching node during the high state, and we stay in the on state until we hit that switching threshold. There's some considerations around how we get it started up and into this mode, but when you're in this mode, if you can predict exactly what that switching threshold wants to be, which there are ways to do that, then you can very accurately set the on time that will force balance. And then the off time is what is doing the voltage regulation. So the off time is basically like a current mode hysteretic controller. So it's looking at V out plus K IC and setting the regulating the output voltage, but the on time is regulating the switch node, regulating the voltage balance. So these two loops in parallel, and why is this nice is because it's extremely hardware efficient. There's some digital supervision that we do to do sort of the threshold guessing, but it is otherwise basically two comparators that we're using. And because it's digitally supervised, there are nice things about it, like you can make it run in constant frequency mode. You can have nice transitions between discontinuous or light load, just DCM type modes. And then also there's a max stress limit. You can make it, if the load current grows too much, you can enter a non-constant frequency. Frequency keeps going up if the load current goes up. That just because you have to do that to make sure the voltage stress doesn't grow. And so there's some nice features of that we studied. The other and more I think also very interesting strategy is we call it modified ripple injection, and it's basically a way to inject the balancing information directly into a sliding mode. And why this is nice, it works for very high order converters. We can effectively make like a fifth order sliding mode. Most of it is very similar to we would call a conventional hysteretic controller. In other words, that where the output regulation loop is based on a reference and a hysteretic. It's just a hysteretic controller, but we adjust the switching threshold or the hysteresis level by detecting the switching node voltage across a state. And if it's low, basically what we do, I'll just say, if the switching node is low, we integrate that and we reduce the upper hysteretic switching threshold level. So it's kind of like a hysteretic controller where we're adjusting the hysteresis value, but only on one side, and only when the voltage of the switching node is low. And that's basically a stability consideration. It's a lot like that peak current mode versus valley current mode. The valley current mode is more stable because you're making a decision on the low state rather than the high state. I'm not going to go into that anymore. But basically, if you do this, then you're going to discharge this less, and eventually it pushes towards balance. Okay, and so what we can show that this speeds from natural balance. It gives multiple orders of magnitude speed reduction of the response to sort of a flying capacitor disturbance or a balance disturbance, and we showed that works. And so I guess I will just bring it back to another example of the same thing. So it's basically the same control concept, but one of the considerations is especially around startup. Actually, sorry, I'll flip back to this slide. There's a lower level here that we will use. So the way I'm thinking about flying capacitor voltage balance and hybrid converters, a lot of it is about nonlinear control, and part of that is because we need to detect when certain things happen because they can be catastrophic. So balance can be a real problem. And so having an extra switching threshold where if the voltage goes too low, we do something different can be important. And so in this particular work, we use that as a startup detection or basically a line transient detection. And so the idea, and this, I won't go too much into this topology, but it's described in the paper, and I really mostly want to focus on control more than the topology. But this was a two-stage cascaded where we used a switch cap front end and then kind of like a three-level buck second end. And we can show it runs in these states where there's like a V/2 here through a second flying capacitor, and then do pulse width modulation, then connect that second capacitor, then do pulse width modulation. That's sort of our normal PWM sequence. But in startup, let's say all the capacitor voltages are 0. What we want to do is only ever charge capacitors. So when these voltages of capacitors are 0, the supply voltage goes up. We want to keep these capacitors connected. They form a natural voltage divider, so they'll sort of pre-charge together, and then they'll charge this capacitor too. And so we only connect in this state and then the PWM state during startup, and that gives us a faster response and allows us to balance the capacitors more quickly. And so in this particular example, this converter had a nice feature where all the gate drivers and bootstrap capacitors were very neatly organized and fully self-powered. There's no external supply for them. They run off the own internally generated supplies. So we could hard plug this converter straight into the 5-volt USB rail with no other additional startup consideration, just hard plug it, and just inductance or resistance in the cable limits the rise time. But the converter could start up, pre-charge all the capacitors, and enter a normal regulating mode. And this is like a 5-volt to 0.7 volt step down within about 10 to 15 microseconds, which adjusted for sort of the switching frequency, it's only like 20 or so switching cycles, something like that. We're fully pre-charged and regulated and operating. So that's a nice example of like using a nonlinear threshold and then a nonlinear control scheme to keep things balanced. And then of course it uses again like it's a hysteretic controller. So the dynamics are fast, so it responds relatively quickly to line transients or sorry, these are load transients, and not much more to say. Just that controller was functional. The main thing is the voltage balance was fast, and we were able to achieve the really rapid startup. And again, this I'm not really talking about the topology per se, but like the also had good efficiency, of course. But so so that's that. I'm going to go ahead and conclude. That's just so I can leave some time for questions. Main thing I want to say is that again, hybrid. I have been working in this field for 15 or probably more years, maybe closer to I hate to say 20 years, but it's really amazing how going from people telling me this would never make sense, or why don't you just build a buck converter, to now it seems like there are very real opportunities for hybrid converters is pretty exciting to me. Main difference is with hybrid converters, you have to consider the voltage dynamics for the control. It's very important for reliability, robustness. Many approaches are possible. And assuming voltage balance is achieved, you can use a lot of conventional control. And so many opportunities are possible. And I'm looking forward to the work coming out of industry and academia as well. And just mentioning again the Power Management Integration Center. So again, this is sponsored by the PMIC. If we're looking, we still have openings for industry members through May to join this June meeting. And so if anyone's interested, feel free to get in touch with me or the rest of us at PMIC. I'll go ahead and open it for questions. So,
okay, and I'll go ahead. Thank you for putting in a couple of questions, and I'll go ahead and read the first one, which is in FCML about driving the gates in the middle flying MOSFETs, both about how to get the bootstrap or other bias for that. But then also interesting is if there is imbalance in the gate driver bias supply, does that, and if that changes the RDS on the FETs, will that lead to imbalance in the flying capacitor voltage?
yeah, it's a great question. And sorry, I'm just having to flip slides. So there's quite some work on that type of thing. And certainly the bootstrapping and gate driving in FCML is an extreme challenge. And same with all hybrids, and something we've spent a lot of our work on, and frankly many others. And there are many schemes to do the gate driving. So whether there's nested bootstrapping, there are ways you can bootstrap one switch from another, from another. There and other methods and ways you can operate them off the flying capacitors. And so a lot of our work ends up being about how to do that. And I didn't really get into that in this particular talk, but certainly yes. So of non-idealities, if your gate drive supply voltage sags, or you maybe even have a systematic reduction in the gate drive supply voltage, that can absolutely lead to an imbalance, because the switch resistance can impact differential switch resistance, and switch timing can impact balance. So certainly it's a major consideration. And so those are quite big things that we work on the implementation side, and not just me, but I should say many people work on that type of thing.
Okay, and while you have the FCML up there, there's another question about it's often used in low voltage applications, but can you comment on whether the same approach can be extended to higher voltage applications? If each capacitor was a 400 volt or in that range, could you get to higher voltages without increasing the number of flying capacitors? what are the limiting factors in going to higher voltage there?
So again, I should say that, flank FCML was invented initially for high voltage applications. So it was a envisioned as a grid interface architecture, so a medium voltage inverter. And so there are many examples of high voltage FCML converters and possibly more um, in the higher voltage power electronics literature. So the trade-offs, there are certainly quite some trade-offs. You need uh, flank capacitors that have enough capacitance, which they can eventually be large, and they are not all rated to the same voltage. So for example, C3 is rated to, in this case, 3/4 of VN, but it gets worse the more numbers of levels you have. And that some of the capacitors may have different voltage derating because of that. And so your capacitance may not be the same in every cycle. So it's quite complicated, but I should say there's plenty of opportunity to have high voltage FCML converters. I'd say they're more widely, so you probably find more high voltage FCML converters than low voltage.
Okay, and one more question about FCML, which is what is the best way to deal with parasitic inductance when, for example, the flying capacitances are off chip in an integrated FCML?
Yeah. So I can't resist, but I have to bring up, so my colleague Robert Palawa at Berkeley has done quite some work on that. We've certainly done quite a lot of work on that. It like any DC-DC converter, my statement is you have to trace out all the commutation loops. So anytime you're transferring energy, you need to know exactly where that energy is coming from, trace out the loop, and make that loop as small as possible. And there are many thought processes around that. We've done some, there's some nice layout structures. I think look at Robert and his students' work. This is an example where I can't really zoom in on it, but this is an FCML where we're working very hard to make that loop small. We do things where we cheat. I guess I'm not going to call it cheat, but we put capacitors directly on top of the chip, which for lack of the resources to buy a $20,000 interposer, this works for us, and we're pretty good at soldering, so we can put capacitors on chip, and that reduces the ES effective series inductance, and so we do that a bit, but that's certainly a problem. I don't have an exact answer for it.
Okay, and we're running out of time, but I want to slip in this higher level question, which is, can you comment on any changing trends in optimal topology selection you've noticed as converters move towards more integration and advanced technology nodes where interconnect and reactive component resistances can dominate efficiency over active device resistances? Integrated cap energy densities might be quite high, but I wonder if potentially higher effective ESR from interconnect, thin plate sheet resistance, et cetera, would diminish that benefit.
So Charlie, this is the problem with when you can do a written Q&A, because that's a lot to remember what that question asked. But what I would say is that sounds very realistic of a number of challenges. Certainly, the interconnect resistance can be significant in an integrated circuit, and we certainly do look at that. And that I think I'm just making some stuff up, but I think it pushes towards simpler topologies. But there's also really nice features of a better assembly processes. And power distribution layers and metallization layers. So I think all of these go hand in hand. And usually if there's a process limitation, people will find that and work on it. And so certainly I see in power integrated circuits, and especially at the very highest performance levels, um, the metal stack ups are getting really interesting. And so there's, hopefully there will be solutions to that. So I don't know if whether it goes towards simpler or more complex. I think we'll just have to see.
Yeah, and I think the other piece of that is the shift towards you don't just optimize based on the active devices, but really understanding the passives and getting the most out of them in the design.
Yeah, and I mean, a lot of our work, frankly, and Charlie, you know this as well, a lot of our work, even in the research center, is also about, we've done a lot of work on winding losses that, those don't show up until you start to look at the metal stack up and really analyze the components, and then you see you might need to do some things differently. So yeah, so holistic design, it really is really the answer.
Okay, and we are over time a little bit here and have addressed most of these questions. So I want to thank everyone for showing up and thank Jason. Thank Jason for a great, insightful presentation.
Yeah. Thanks, everyone. Thanks for coming.